Today we're going to move further with atomic structure and look at the development of modern atomic theory. From our earlier discussions, we know that atoms are composed of electrons, protons, and neutrons. The protons and neutrons are located in the nucleus of the atom, which is the central core of the atom. The electrons are in the space outside the nucleus, and we call that space the electron cloud. So today what we're going to be looking at, our essential questions for the day, would be how was light used as a tool to help understand atomic structure, and secondly, how are the electrons actually arranged in the electron cloud. We will only begin to get to the answers to these two questions today. The podcast that follows this will actually give more detail into the answer of especially the second question. To understand how light was used, we have to go back to Ernest Rutherford. You've watched some videos on atomic history and Rutherford's planetary model. So I want to just think about what was Rutherford's model. First, we had Rutherford's model included a central dense positively charged nucleus, and we actually can go along with that still being a central idea today. So we can say that that's a good idea. We still go along with it. Electrons orbit around the nucleus like planets around the sun. So you've all seen some sort of model of the atom in an earlier science class where we've got a nucleus, then around the nucleus we've got electrons that are going to be in concentrically larger spaces outside the nucleus, making what sort of looks like a model of the solar system. Okay, we do believe that the electrons, still to this day believe the electrons are outside the nucleus, but maybe not in that arrangement. So we end up with this model of the atom. This is helium specifically, with 2 protons, 2 neutrons, and 2 electrons in the electron cloud. Now, Rutherford's model was based on experimental evidence. That was the gold foil experiment. This was based on radiating gold foil with alpha particles and watching the scattering pattern of the alpha particles after they collided with the gold foil. There was, however, a series of problems with Rutherford's model. The problems with Rutherford's model included the following. First of all, if we had, let's say, an atom such as, let's make it hydrogen, which has just 1 proton, simplest atom, 1 proton and an electron out here, and let's say that electron orbited in a circular pathway around the nucleus. So we're going in this direction. One of the problems with this model, which Rutherford proposed, is that when the electron moves, if it's moving in a circular pattern, it's undergoing what we call in physics acceleration, because it's moving in a circular path. Acceleration means it's changing its speed or changing its direction of motion. So if it's anytime we have anything moving in a circular path, we have an acceleration occurring. This accelerated electron should radiate energy in the form of light or some form of electromagnetic radiation. And in general, we know that doesn't occur. So we can say that this model, what it predicts in terms of this moving electron moving in a circular path, that doesn't seem to hold true. The other issue is that if the electron is radiating energy, then it's losing energy. So as it loses energy, then eventually this path should lead toward a collapse of the atom with the electron colliding with the nucleus, and really know what would happen there, but it would be a destruction of what we know of as atoms. And we know that in general, matter seems to be rather stable. You look at your table or your chairs or your books or you, and everything seems to hold together pretty well without self-destructing. So there were more problems, but those are just a couple of examples of problems with Rutherford's model. Rutherford, by the way, pointed out those problems. He was a genius, so to speak, and he knew that his model had problems, and he presented those as places for more research to lead, to find answers. So our next individual after Rutherford made some major contributions. That is Niels Bohr from Holland. He got a hint on electron arrangements, how they were actually arranged out here and what they did when they were out there, by looking at light that was emitted from atoms at certain times. One thing we can say is that even though electrons don't continuously emit light, which is what they would do in this model, they do sometimes emit light. And to understand how this light-emitting atom works, we need an understanding of waves. So that's where we're going to go in the first part of this presentation, is looking at waves. So what exactly is a wave? A wave is a rhythmic disturbance that transfers energy. Notice that it is not a structure, it's not an object, it's something that's going to involve transferring of energy. It results from vibration of an object somewhere, and that vibration has an effect on the surrounding matter. That matter could be air, it could be water, it could be a string on a violin, it could be could be my vocal cords vibrating. And so we end up with this. For instance, we have an object here, a sphere rotating and vibrating in some water, and as it vibrates, it's disturbing this area, it's disturbing the water, and the water disturbances move out away from the center, creating these circular waves. So when we look at a wave, we can measure certain things, and there's certain terminology we need to be able to use consistently, so I'm going to make sure that this is all defined for you. First of all is the wavelength of a wave. Okay? And that wasn't quite what we needed. The wavelength of a wave is going to be, as is labeled right here, is going to be the distance between adjacent crests. Okay? So a crest would be the top of a wave here, here, and here's the second crest, and a wavelength would be the distance between crest and crest. We could also say that it's the distance between trough is the low part, between trough and the adjacent trough, or really anywhere on here. We could say from this point, which would represent 0 degrees, to this point, which would represent 360 degrees. So we could we have that the wavelength is actually the distance between the same point on adjacent waves. And this represents one wave, and this represents a second wave. So we're measuring from the crest of the first crest on the wave to the first crest on the second wave, or from the trough on the first wave to the trough on the second wave. Unit of wavelength in SI is meters. But we can also have other units like centimeters and nanometers and angstroms and all sorts of different length units. The amplitude of a wave measures how far the wave rises from the x-axis. So if we split this or bisect this sine wave here with an x-axis, we can say that the amplitude is how far from the x-axis to the peak of a crest or to the bottom of a trough. So this would also be an amplitude. Amplitude represents energy. How high the wave is a function of energy. This is true for mechanical waves. And mechanical waves are waves that require matter to be able to move. So, for instance, waves on a string, waves in water, sound, all these would be mechanical waves. So the further the wave moves in terms of its height or depth away from the x-axis, the more energy is possessed by the wave. From a unit standpoint, normally we measure this in meters because we're just saying how high the wave is, not necessarily how much energy it has. The true unit, though, should be joules. Joules is the energy unit. So if we're truly looking at energy, we would say joules or some sort of energy unit. But again, usually we just make it meters, and we say that the greater the height in meters, the more energy that the wave has. And again, with meters, it could be centimeters or nanometers or whatever. Okay, the frequency and the period. Frequency is how many waves pass a point per second. Period is a similar idea, but period is how long for a wave to pass a point. This is a time. Okay? Frequency is more often used, but we can say that frequency is going to be measured as far as units in waves per second. But since wave is not really a unit, wave is a structure that we have here, this is sometimes written as just 1 over second. The 1 over second unit is called the hertz. And of course this is time, so this is just measured in seconds. So if we have frequency in 1 over seconds and we have time in seconds, we can say that period, which is called T for period, F for frequency, period is equal to 1 over frequency. Period is the reciprocal of frequency. Or it's equally correct to say it the other way around. Not only is period the reciprocal of frequency, but frequency is the reciprocal of period. Unit again, SI unit is the 1 over second or hertz unit. All right, then we have wave speed, another measurable property of waves. And the wave speed is looking at the distance traveled by a wave in a unit of time, such as the number of meters traveled per second, just like any other speed. The equation for this, let's see if I've got this here, I do not. The equation for this, wave speed, general wave speed is V, is equal to distance per time. The other way of putting it in terms of wave features is speed is equal to wavelength times frequency, or wavelength per period. Now, symbols for wavelength and frequency. Symbol for wavelength is sort of like an upside down Y. This is the Greek letter lambda. And frequency, we're just going to call F. So we can say V is equal to wavelength times frequency. Or it could be equal to wavelength divided by period. Or just simply distance divided by time. All right, we have a couple of different types of waves. First of all, we've already mentioned the mechanical wave, and we also have electromagnetic waves. A mechanical wave is one that requires matter. When I say it requires matter, that means that in order for it to move through space from point A to point B, there has to be something there to carry it. So this matter could be air, if we're talking about sound. It could be a string, if we're talking about a guitar. It could be a vocal cord. Actually, that would just be air. It could be water, which would be, of course, water like waves on the ocean. Electromagnetic waves do not require matter. Doesn't mean that there can't be matter, it's just that they don't require matter. So that means they can pass through vacuum or through empty space. Examples of, well, I already gave you some examples of mechanical waves, but examples of, which would include, just give you some names here, sound, for instance. We could also say ocean waves. For this, electromagnetic waves or electromagnetic radiation. That includes things like visible light, X-ray, infrared, and so forth. And we'll be listing quite a few of these eventually. Electromagnetic waves have some differences from mechanical waves. One of those differences, if I can get this thing to stay, one of those differences is that it doesn't require matter. So one doesn't require matter. Number two, it has two parts, which would be electrical and magnetic. And three, I won't put this in here, but we'll talk more about this later. Energy is dependent on frequency. For this type, energy depends on amplitude. Okay. Most of the things regarding waves of either type would be handled the same way, such as calculating speed, but for mechanical waves, there's definitely a difference from electromagnetic wave. This is actually the type of wave that we're going to spend the most time talking about down here. One other major factor down here that we should put in: constant speed. That constant speed is 3.00 times 10 to the 8th meters per second. Speed of light. All electromagnetic radiation travels at the speed of light, and the symbol for the speed of light is c, for constant. Now, waves have certain, sometimes it's difficult. This is a problem with chemists and physicists in the late 1800s and into the 1900s. Sometimes it's difficult to tell whether or not something is matter or energy. Matter is made of particles, so we can say particulate. And we can also have energy, which is thought to be wave-like. So generally speaking, when something moves through space, it's either moving as a particle, such as a baseball flying through space, or as a wave, such as energy traveling through water on the ocean, making the waveform that you typically see when you go to the beach and see waves. There are certain properties that when we look at a phenomenon, when we look at something happening, that allow us to diagnose something as being wave-like. And if it's wave-like, that tends to mean that it's spread out and like energy. If it's particle-like, then that tends to mean that it's matter. So let's look at a few of these, because this was an issue with light as well as some of the particles like electrons that we've dealt with. Okay, first of all, first of the properties that you can look at, and if this happens, it's a property of a wave, is reflection. Reflection just simply means bouncing off. I think everyone understands what reflection means. Second is refraction. This is a change in speed and direction when a wave passes through media. Media means what the wave moves through. And then third is something called diffraction. And diffraction means bending of a wave around a barrier. And here's an example of diffraction. You can see that we have this source of waves here in the center. It's passing circular waves off to this barrier. When it hits the barrier, there's an opening in the barrier, and that creates a little bit of a disturbance. The wave can't pass completely through. So what this does is creates a new disturbance, which provides a source of more circular waves. And the end result is that we get circular waves that pass everywhere around the barrier. So the waves are bending behind the barrier. Light and all electromagnetic radiation display all the properties that are characteristic of light being wave-like. Okay, so it's been considered for many years, since the 1600s or so, that light and all electromagnetic radiation like X-rays and gamma rays and ultraviolet light and infrared and so forth, radio, microwave, light has wave properties. Another interesting feature of waves is what happens when waves interact with other waves. When one wave interacts or collides with another wave, two things can happen: constructive interference and destructive interference. As an example, let's suppose we have a string that is attached to something. Let's move it along the x-axis. And let's say that we've got some sort of height here, maybe 1 meter and -1 meter. Okay, so we've just got those heights labeled. And let's say that we have a hand out here that generates, maybe lifts up very quickly and produces a wave pulse that's going to travel toward this barrier. We call this a wall over here. As the wave pulse travels, eventually it's going to collide with the wall. When it collides with the wall, it will reflect and come back down the other side. And so what happens, let's say that this is 0.5 meters and that this is -0.5. What happens when they actually meet in the middle? When they meet in the middle, what's going to happen is that we're going to have a positive 0.5 wave sitting on top of a negative 0.5 wave. These waves are going to add algebraically. So when they add algebraically, that means we've got a positive 0.5 plus a negative 0.5 meter And the end result is that at the point where they meet, they're going to cancel each other out. Waves cancel. This is destructive interference. Destructive interference means the one wave is destroying another wave as they encounter each other. In reality, they don't destroy each other. At this point where they meet, if we have a positive 1/2 and a negative 1/2 wave pulse, this one moving in this direction, this one moving in this direction, what they actually reduce to at this point is just a flat line or zero. If, on the other hand, let's suppose we have a scenario like this, where we have a, let's call this a positive 1 moving in this direction, and maybe we've got on this string we've got a negative 1, a positive 1, excuse me, moving in this direction. When they encounter here in the middle, positive 1 plus positive 1 equals positive 2. So what's going to happen is that if this is positive 1 and this is 2, when these waves meet right here in the center, what's going to happen is that the wave's going to get bigger. So this is going to be a positive 2. This is constructive interference. Wave building. So on this slide we're going to look, and we've actually already talked about this, we've looked at some of the unique properties of electromagnetic radiation, so I'll just reiterate them here, and doing that because we're going to primarily be talking about electromagnetic waves. So first of all, the speed of electromagnetic waves, the speed of light. The relationship between frequency and wavelength. Speed is equal to wavelength times frequency. And the relationship here is that if this value is constant, as the wavelength increases, the frequency has to decrease. So wavelength times frequency equals a constant. That means that wavelength is inversely proportional to frequency. So as wavelength increases, frequency is going to decrease. The medium. Medium is not required, but there could be one, such as light passing through someone's glasses or a lens. Energy proportional to, rather than amplitude, energy proportional to frequency. High frequency equals high energy. That also means, based upon this relationship, that high wavelength was low energy. And you can see why we might want to talk about frequency related to energy, because they tend to go together, whereas we have an inverse relationship between wavelength and energy.